Alright guys, so this is going to be presumably the third and final video on my famous math series. There might be more in the future that I might do if I become interested or if you guys really like it. But yeah, so this last one's going to be the Gaussian integral. So there's this famous curve in statistics called the bell curve. Looks like this. Has asymptotes on both sides. And now, so if we, so people for a long time wondered like the area under the curve, right? And so the equation for the bell curve is e to the negative x squared. And people wondering, okay, if I go from negative infinity to positive infinity under the curve, will that answer converge? And if it does, what does it converge to? You might think, okay, let's just take the integral from negative infinity, positive infinity, dx. But when you do that, you actually can't integrate that. There's no elementary derivative, antiderivative that you can use the fundamental theorem of calculus on. So what do? Well, first we just define this integral as I, and now let's square it. So I squared will be the integral from negative infinity to positive infinity, integral from negative infinity to positive infinity. Now we have a double integral in terms of both x and y. So that's what it means to square it. And now the trick is just going into polar form, right? So I'll just draw this, the basis for polar form. So if we have some radius r and an angle theta on the xy plane, and let's say we have another ray, now we have some change in the angle, called that d theta, and now we have this region right here where we want to be in, and we also have this change in r, so this as much as r, this right here would be dr. So we want to know what this area is. So so first we have this part right here. Let's just say area is length times width, right? So we consider this is the length, this is the width. Remember, this dr is infinitesimal. So even though it looks like this and this is way bigger, it's really not. It's pretty much the same size. So what is the length? The length is just the arc length. So the arc length is S is arc length equals R theta. And the area, it would just be the arc length S times dr. So that's length times width. So area is going to be, well, this is normal S length. But now this S length is for this arc here. Now we're here when theta is actually d theta. So area of the sector will just be r dr d theta. Because this is actually analogous to theta. Yeah. So now that we have that, so now this integral is that. But what is r? So let's define r squared to be x squared plus y squared, because r is just the hypotenuse of this triangle with x and y. That's what we see here on the plane. This is x distance, and this is y distance, and then we have r, the radius. And we still have the same data here. So now that we have that, this integral becomes, so now we're in the r theta world, right? So negative infinity to positive infinity on the xy plane, and both integral and both on the bounds of both integral, right? That's actually the entire xy plane. So you want to cover the entire plane in theta. I mean, in the polar form, polar coordinates, right? So r is the radius. So that's one plane we have to cover, and theta is another plane. So to cover all the theta plane, we have to go in a circle. So all we got to go for theta is just 0 to 2 pi. Okay. And then for r, well, r is just going to be rotating with it. So notice the angle theta is what r makes with the plane. So as theta increases, r swings around. So r will be rotating as well. So for r to cover the entire plane, it really doesn't even have to, it only has to go from 0 to infinity to cover the entire plane. Now we just sub in. So remember how it's r dr theta. So there's an r, then there's going to be e to negative r squared. Then we have dr d theta. Also, if you don't like the geometric way of doing that, you can just take the Jacobian. So we define Rx to be R cosine theta and Y to be R sine theta. Then we take the Jacobian. I don't like writing the J. I'm just going to just take it. So the Jacobian is we use absolute value of the Jacobian, by the way. But it's the determinant of the matrix of the partial derivative. So we do partial x with respect to r, and then partial x with respect to theta, and then partial y with respect to r, and then partial y with respect to theta. So this is just going to be, so now we're doing it with respect to r. So this is just going to be cosine of theta. Now if we do it with respect to theta, this is just going to be r. Well, it's going to be minus r. Oh, oops, yeah, clicked off. Please. Okay. So it's going to be minus r sine theta. Now we do the same thing for y. So with respect to r, it's just sine theta. Jesus, what happened? Now we do it with respect to theta. It's going to be r cosine theta. Now if we do this is going to be r cosine squared of theta plus r sine squared of theta. So that the Jacobian is just r. So now that we have that, that's another reason why it's going to be r dr theta and not just dr d theta. But anyway, that's just extra. That's just if you don't accept the geometric way of doing it, which is the calculus way. So it's going to be r dr and not just dr d theta. A little sidetrack. Anyway, now that we have this, we just can do a normal u sub. So we said let u equal r squared. So du is going to be 2r dr. Okay, so divide that 2 over, so that means du over 2 is going to be r dr. So we have this, we have r dr. So we can replace that. And actually, we can just keep it we can actually move the bounds in the u world. So when r is 0, u is 0. When r is infinity, u is also infinity. So the bounds stay the same. And now, what we're going to have is e to the negative u over 2 du d theta. Now, remember, all this is still equal to I squared. Okay. Now that we have that, we just do what we always do. So that's going to be negative e to the negative u over 2. And now we just evaluate that from 0 to infinity. So we end up at infinity, we're going to have just 0. And then we're going to be plus a half. Because e to the 0 is 1. So now finally we have the integral from 0 to a half. I mean, what the heck? 0 to 2 pi of a half d theta. Okay, that's just going to be theta. So that's going to be theta over 2. Evaluate that from 0 to 2 pi. So that's going to be 2 pi over 2. That's going to be pi. Pi minus 0. It's just pi. So that all that's equal to I squared. Now notice we was talking about the original integral. So all we got to do is just take the square root. So I is going to be root pi, and it's positive root pi because the area. I didn't draw it actually. Because the area under the bell curve is above the xy plane, so it's positive area. So yeah, that's a famous integral called the Gaussian integral, and that's the area under the curve, square root of pi. So it's pretty crazy.